Good morning. Today we're going to be talking about section 5.9 entitled Solving Equations by Factoring. Let me take a minute for a little background. Factoring. Why do we spend so much time factoring in a first and second course like this one in algebra? Well, we spend pretty much all of chapter 5 on different techniques of factoring, GCF factoring, trinomial factoring, difference of squares type factoring, and there's other types of factoring also. Why do we spend so much time factoring? And the major use of it is to solve equations of higher degree. Well, what do I mean by higher degree? Well, the degree greater. Let me write that down. Hang on. By higher degree, I mean degree greater than 1. Well, for example, if I have an equation, very simple equation, 2x minus 3 equals 0, we can solve this very easily. 2x equals 3 and x equals 3 halves, of course. We did this in chapter 2 and chapter 3. This is a degree 1 equation. 1 meaning the highest exponent you see on any variable is, of course, 1. Well, what if we get to something, an equation with a degree higher than 1? Let's give you a degree 2 equation. Let's say x squared plus 5x plus 6 equals 0. If I ask you to solve this, well, we can't solve this as we did in chapter 2 with simple addition, subtraction, multiplication, and division. There's no way to isolate x all by itself because you have two different degree terms. These are unlike terms and cannot be combined into one expression, so we can't solve with previous techniques, but we can solve it with factoring. I'm going to solve this by factoring. Alright, if I see this equation, x squared plus 5x plus 6 equals 0, well, I can't combine unlike terms, but if the trinomial is in standard form, I can break it down to a product of two binomials, I think. I can break this down as x plus 5 times x plus 1 equals 0. And notice now I've got a product of factors equaling 0 on the left-hand side. I can invoke what I call my zero product property or zero product rule, which says if you've got a product equaling 0, then either A equals 0 or B equals 0 in this simple example. So what I can do is take each of those factors and individually set them equal to 0. So what I end up with is a degree 2 equation that has branched down to two simpler degree 1 equations, which now I can solve as we did before in chapters 2 and 3. I get x equals minus 5 or x equals negative 1. Alright, hence we have quite easily solved the puzzle on how to solve equations of degree 2, or as we'll see, even higher degree, we'll talk about later in this section. Another example. Solve the following equation. 3x squared equals 6x. Well, what am I talking about, you're thinking? Well, you don't have a trinomial equation. You do have a degree 2 expression, but you don't have a trinomial equation. Well, probably the first thing you want to do in equations of this type is get it in standard form. Arrange terms in decreasing degree, and I suppose the tendency would be to get all your terms on the left-hand side of the equation equaling 0 on the right. Now, notice I don't have a trinomial here, but I can still factor it. That's a GCF factoring, is it not? I can factor out a 3x out of that expression. I get 3x times x minus 2 equals 0. So I can still factor using GCF factoring, and again I now have a product of factors equaling 0. I'll invoke my zero product rule. I'll claim either 3x equals 0 or x minus 2 equals 0. Well, if 3 times x equals 0 on the left-hand branch, well, I could be real formal about this. I could divide both sides by 3. The 3's cancel out, and x equals, well, 0 over 3 is 0. Any fraction with a numerator of 0 is equivalent to 0. Or, on the right branch, of course, x equals positive 2. Alright, so I've got a degree 2 equation with 2 solutions. You could have at most n solutions for an nth degree equation, as we'll see, and we'll jump to the next example. Let's see, solve. X equals 6/7 x squared minus 3/7. Oh my, what are we going to do? We've got fractions to deal with. Well, probably the first thing you want to do is get rid of the fractions. I can multiply both sides of this equation by the least common multiple of all the denominators, which here, of course, is 7. All the fractions will go away. I've got an equivalent equation with all the fractions disappearing. Now, you've got to apply your distributive law. This times 7, well, the 7's will cross cancel, and I've got 6x squared resulting from this product minus, well, you've also got to multiply 3/7 times 7, and of course the 7's cross cancel, and I'll get minus 3. Alright, so what I'm going to do is put everything over on the right hand side to get it in standard form. 6x squared minus 7x minus 3 equals 0. I think I see something happening here. Let's see, can I factor this? 3x, 2x in the first slots. Let's see. 3 and 1, I think will do it. If I get a minus 3 and a plus 1, let's check it out. First product is 6x squared, that's fine. The outer product is minus 9x. The inner product is plus 2x, and that indeed adds up to a negative 7x, and minus 3 is the last product. So let me rewrite that. I factored that. Standard form expression on the right hand side, doesn't matter if it's on the right or the left. An equation is an equation. I will now take this equation and branch it off into two degree 1 equations. 3x plus 1 equals 0, or 2x minus 3 equals 0, and of course I can solve these hopefully easily. So x equals negative 1/3 from the right branch, or x equals 3 positive 3/2 on the other right branch. Okay? Alright, so even some nastier degree 2 equations we can pretty easily solve by factoring. I think I'm going to need more room here. Let's see. Solve. 5x cubed plus 13x squared equals, minus 6x. Oh, let's see. This was inside of your homework list. It starts out equals 6x, okay? And you're thinking this is not a degree 2 equation, this is a degree 3 equation. Well, degree 3 expressions can sometimes factor, so we may be able to solve this one by factoring as well. Alright, first step, probably a first good step in all these problems, to get your polynomial expression into standard form. In other words, arrange your terms in decreasing degree equaling 0. Alright, so we want to solve, and solve by factoring is our only technique here, so I'm going to try to factor the left-hand side. Well, I don't see... Well, let's see, what can I do here? I can factor out a GCF. Let's look for... You should always look for a GCF first. As we've said many times, look for GCF, and I can factor out an x, can I not, from that trinomial expression, 5x squared plus 13x minus 6 equals 0. So I factored a GCF out, and I think I can factor this even further. let's see, x times 5x minus 2 times x plus 3. Let me check that. 5x squared is the first product. 15x minus 2x is 13x, and minus 6. Yes, so that indeed does factor completely as I've written it here in this last step. Well, that zero product property holds no matter how many elements of factors you have in your factored expression. So this will branch off to 3 degree 1 equations. So I'll get x equals 0, or 5x minus 2 equals 0, or x plus 3 equals 0. Don't forget to include x equals 0. X is a factor here in your factored expression, so x equals 0 is going to be a viable solution. So as final answer, I'll say x is 0, or 5x minus 2 implies x equals positive 2/5, and that's a possible solution. Or, of course, from this third branch, x equals minus 3. So notice I started with a degree 3 equation, and by this factoring process, I ended up with 3 solutions for x, and all of them can be checked, but to save time, I won't check them here. Alright, so we've done some degree 2 equations, we've done a degree 3 equations. Now I want to talk about a degree 4 equation, and even those can be solved by factoring sometimes. Solve minus x to the 4th plus 5x squared minus 4 equals 0. Alright, it's already in standard form. I've already got the terms all lined up on the left-hand side in decreasing degree equaling 0. It's always easier to factor when you have a lead coefficient that is positive. So what I'm going to do is factor out a negative 1 here. You can always factor out a 1. You can always factor out a negative 1 to suit your liking. So I get this resulting expression, minus 1 times x to the 4th minus 5x squared plus 4 equals 0. Alright, I'm going to multiply both sides by negative 1 now. I can do that as long as I do it to both sides of the equation. If I multiply both sides by negative 1, well, the nice thing is 0 absorbs any factor, and negative 1 times negative 1 is positive 1. So I get this resulting, perhaps simpler expression with a positive lead coefficient. Of course, if you wanted to start here and just multiply everything through by negative 1 a little more informally, that's fine. In any case, we end up with a degree 4 equation in standard form with a positive lead coefficient. Of course, I'm going to factor this now. I think I see if I have x squareds in the first slots, and I can factor this as x squared minus 4 times x squared, looks like minus 1, does it not? Check it. The first product is x to the 4th. The outer product and inner product do indeed add up to minus 5x squared, and the last product is, of course, positive 4. Alright, so I have factored the left-hand side, but notice there's difference of squares here, there's difference of squares here. I can factor this again, and I'll get x plus 2 times x minus 2 as the breakdown of x squared minus 4, and x squared minus 1 breaks down as x plus 1 times x minus 1. So now I've got a chain of 4 prime factors multiplied equaling 0, and of course this will branch off to 4 degree 1 equations. So I don't know how formal you want to get here. Let me write it out. Alright, 4 degree 1 equations, which of course can be easily solved. X equals minus 2, or x equals positive 2, or x equals negative 1, or x equals positive 1. So we have a degree 4 equation that has come up with 4 unique solutions for x, and they can all check out if you desire to take the time and plug them in to this original equation. They should all check out. You've got 4 solutions for x in that degree 4 equation. Now you can have as many as 4 solutions in a degree 4 equation. You could have less than 4, but you can't have more than 4. Okay? Oh, let's see. 2 more I believe I got on the list. Solve a cubed minus 18a squared equals negative 81a. It's a degree 3 polynomial equation. Alright, first step, get it in standard form, because I'm going to look to factor this. Alright, so let me arrange the terms in decreasing degree. I will add 81a to both sides, and I get this resulting degree 3 polynomial equation. Of course, I have a GCF of a here, so let me factor out an a. And once I factor out a GCF of a, I then see that's an 18, a negative 18 there. Once I factor out a GCF of a, I think I see a trinomial, which will factor again. I think that's a. Let's see. If I pick a's in the first slots, oh yes, if I get 9s, put 9s in the last slots, and minus signs in between. Let's check it. A squared is the first product. Minus 9a, minus 9a are the inner and outer products, and they do indeed add up to a minus 18a. And plus 81 is my last product. So indeed it does break down as a minus 9 times a minus 9. I think I see something coming up the road here. Maybe you see it too. Alright, so I've got a list of 3 prime factors being multiplied equals 0. Don't forget to include a equals 0 in your list. A is a factor, so a equals 0 is a solution. Or a minus 9 equals 0. Or a minus 9 also equals 0. And of course, these two are the same equation, which results in what our book would call a repeated solution of a equals 9. Alright, now I don't insist that you write the solution a equals 9 twice. I just want you to be aware of the fact that sometimes you can have a repeated solution in these problems here. The repeated solution is a equals 9. So from my 2 solutions in this equation, a equals 0 or a equals 9. So we had a degree 3 equation. We started out with a degree 3 equation, ending up with 2 solutions, a equals 0 or a equals 9. Alright, one more today. I'm going to try to squeeze it in here. Solve 64 t squared minus 81 equals 0. Well, it's already in standard form. I've only got 2 terms here. It's a binomial. It's a degree 2 binomial. So I'm not going to be able to factor it as a trinomial, but I think I recognize this as a difference of squares. So I think I can factor this as 8t plus 9 times 8t minus 9 equals 0. So I can still factor it with my difference of squares factoring, and again my 0 product rule holds. I will take that degree 2 equation and break it off into 2 simpler degree 1 equations. Alright, and hopefully I can solve these easily. If 8t plus 9 equals 0, that means t equals positive 9/8. Or if 8t, hang on, I made a mistake here. Let me grind this out since I made a boo-boo. If I subtract 9 from both sides and then divide by 8, as in chapter 2, I get t equals negative 9/8 as a solution for t. Or, of course, 8t, I'll add 9 to both sides and then divide by 8. The 8's cancel out here, and I get t equals positive 9/8. So again, two solutions, fractional solutions, but solutions nonetheless for this degree 2 polynomial equation. Alright, we'll call it a day here, and this concludes section 5.9, solving equations by factoring.